very different, right?
Okay.
Okay. Anyway,
So it's 8:30 now. So let's start. Hi everyone. Hope everything goes well with your last week lecture. Um, if you, oh, hi Professor Wu. Nice to see you here. If anyone has any questions about the lecture 5, the external forcing, so please feel free to read them up here. And for those who haven't attended the last meetings, so you may go to the YouTube channel. So we create a channel and post all our online discussions there so that you can review them. Uh, and also for the questions that raised by other all students, we also summarize all the questions and put the answers on the discussion board in the My Course of University of Massachusetts Dartmouth website. So please feel free to review them. Is there any new questions about lecture 5 or other lectures?
Uh, I have a question about lecture 5. So
Yes, please.
can I share my screen?
Yes.
Okay.
you know, Siqi better go to the course side so we know which lecture 5 we're talking about. Okay.
Oh, okay.
Yeah.
Okay. Can you see?
Yeah, we can see that.
Yes.
Okay. I've I've never actually done nesting myself, so I'm worried this question might be too basic. So when nesting between unstructured grids, common nodes are shared, and I've sometimes seen cases where multiple layers overlap, not just a single line, but several layers of mesh. And I think this could help interpolate different physical processes like waves, elevation between the two grids. But a wider overlap does not seem to necessarily mean better results. So, my question is, what criteria determine the optimal size of the common boundary when connecting unstructured model grids?
Siqi, you want to answer the question?
Oh, sorry, Dr. Chen, I'm not uh, able to answer this one.
Okay. So the criticism to decide the size of the nesting really depend on the question you study. Okay, so first things you want to make sure location of the nesting boundary, not only for size. You want to show what located area, what area you should be nesting, start nesting, right? So you had to consider two case, dependent case study. For example, you want to start for tide driving motion, like wind driving motion. Your boundary can be close to the coast. It not really matter because now you do the one-way nesting, you have the larger domain model driving small domain model, right? So the criteria, so you want to make sure reflection from small domain to big domain smaller. But you do the one-way nesting. However, if you had a river plume, for example, had a coastal river plume come out, right? The water can be reached to the boundary for certain time. So if you do the one-way nesting, so your boundary condition be changes, right? Not only for tide, also have fresh water. They come from inside to outside. So then your one-way nesting boundary can be the problem. So in this case, you have to extend your nesting boundary outside the region, make sure the freshwater plume not touch your boundary. That's why, where you should set about a nesting boundary depend on question you want to have. The second thing is you also have to consider about the transition of your grid, right? For example, when you do a very close region, you get a very high resolution. So if like a more tight driving water don't matter, but when you do the deep ocean, some region there, so you find, they got a lot internal wave. High frequency internal wave can be created with a high resolution model, right? But then probably, your coarse resolution model not result is kind of internal wave, because internal wavelength, minimum, maximum length, minimum wavelength you can resolve in terms with 2 delta x, the 2 cell, right? Like you wake up high, you get low, right? So in this way, so if your resolution become high, your internal wave, the wavelength becomes shorter. You get a short wave come out from your high resolution domain. So when you wave propagated from outside, you don't want the nesting the model and the two very similar grade, because if you have because if it's too close, this internal wave can be projected out of boundary, because you get a one-way nesting, right? You don't get a two-way nesting. So then your boundary come from larger domain model, but small domain cause additional wave from propagation from inside to outside. So then your boundary can be accumulation energy. Right? In this way, you have to, two way you can solve the problem. One way you should make it agree transition from small to bigger. Right? Like you look like a left side, you show the picture, small domain, larger domain. I teach my students there said, when you numerically, for example, shallow water equation, you have a surface gravity wave propagation speed is a square root of GH, right? So proportion of gravity forcing proportion your depth, right? So then, however, when you make a model with a just a linear equation, when you try to solve the linear gravity wave equation into the numerically, no matter what method you use, the gravity phase speed changes. Before your gravity phase speed, like phase speed equal to square root of GH. Now you have a resolution, depending on your model resolution. You look at the right side, they will times like square root, like a ratio. Okay, sine like a k like a wave number, there's the x resolution, depend on the vertical ratio. So that means what will happen before your wave speed is not a function with the wave number, wavelength, right? That's why your wave is now your wave speed depend on the wavelength. What happened? That's why you had a wave is dispersed, right? Dispersed. Before is non-dispersed wave, but you change numerically, you become a dispersed wave. Energy will losing. You see me? So then this kind of dispersion way depends on resolution. Resolution bigger, okay, this wave speed can be different with resolution smaller. Right? So then the resolution changes, the wave propagation speed changes. Because numerical method not always result of true physics, right? There are numerical error inside. This error causes wave propagation speed different. Okay, in this kind, so if you have a two grade nesting together, you jump to small to high directly nesting, so you get an energy accumulation. So then that's the right side of the picture show you. So you get a graded transition for high to low resolution, big model grade. So you like the wave propagation speed, because it's not the correct way, at least they have the same consistent numerical wave propagation speed. When you reach to the boundary, your speed is same as your larger domain model. This way you don't have energy accumulation at the boundary. So that's the reason you use unstructured grid, you can do this kind of transition, right? If you structure grid, you're not able to do that. You see me? That's the reason for unstructured grid better than structured grid. That's the reason. Okay, but MIT group had I know there's a professor come from Harvard University. They said that we can do the same thing. Okay, he said we do have energy accumulation as the structural grid model. So then they know how much energy can accumulate it mathematically. So then they had some conservation subroutine to let the dissipation error to the every other place, small side. So this way they can run, they can run for the force back for a couple times, like some people run 40 times, they can make a resolution, they can make energy can propagation out, not accumulating. That's correct, right? No problem. You can do that. But if you do the forecast model, every time the boundary condition, you have to iteration many times to get energy out. That's hard, right? Though some other people doing, they run the model a certain period, then they reset the boundary condition again, rerun again. Just had a, restore reaching boundary for certain period. Okay, so that's why you ask me, so what are criterion? The criteria really depend on the question you want to study.
Mr. Chen, so that common boundary location should not located where, for example, the slope is, I mean, if the mathematical slope is strong.
Yeah, too steep region not very good, because too steep region, because if you the slope region, you get a lot internal weight itself, right? They get an internal weight reflection, because you look about internal weight reflection. If water non-stratified, barotropic, you don't worry. Okay, because non-stratification no sigma error. Sigma error only caused by the density grading, but the density grading not caused by the sea level. Right? That's why you slope top bottom topography. So because the barotropical motion only driven by sea level, like air pressure, also the sea level grading. That's not the cause sigma error. Your model can run nicely. But most error come from density grading on the slope. So then density grading you can cause internal way. So you don't want to put your nesting boundary on the slope region, right? So because this got a big change in the wave propagation, energy propagation. So that's why any kind of numerical, like a reflection internal way, it can cause a model boundary problem.
And
Okay.
second question is, the wider the common boundary, the better?
Not really, okay? If you get a wider boundary definitely wider boundary condition, you can fill out a lot for low frequency, so short wave. Just because every wave number you can resolve is minimum is a 2 delta x resolution. That's the wavelength you can resolve. So then what happens if you have a much coarse resolution wider? So you only can resolve the long wave. Most of the short wave can automatically filter it. But however, you have to consider another problem. You probably not get the wave correctly. Right? You get the wavelength probably too longer, your wave probably too slow, but probably too fast.
Right.
No, so that's the case like climate change model. So why do people don't trust the climate change model? Okay, so reason because of downscaling issue. If you had a climate change, for example, you had a water pollute. You for example, you dump the water from the South Korea coast, right? So you have a climate change model resolution 0.5 degree. So that means one time step. Your polluted water come from Korea coast, go to 0.5 degree. Okay, can go to Japan. Just one time step.
Yes, right.
Right? So if you make a skin, it's like express skin. You only couple seconds, your water can really go to like a 0.5 degree. So this way is not correctly. So that's why a lot of climate change model, you not trust much. I read one science paper, don't trust all science paper, right? So then, so they said Hawaii coast. They found Hawaii coast, they had some sensor changes, whole global changes, right? So they used the model predicted. They said, okay, in the North Pole region, the pressure changes and a couple time step, like East China Sea, Japan Sea can changes. All this caused by the coarse resolution. Another thing recently, Japan and China had a conflict about like a nuclear pollution issue, right? Like Japan had a nuclear, leaking problem. So they dump a lot of water into the ocean. So
Yes.
the Chinese scientists use our model, FVCOM model for other model to like news said, oh, this water really can pollute the China very quickly about a couple months. But then you look at the resolution they choose. They choose two things wrong. One is resolution, coarse resolution. Another thing, they make the Huang diffusion very big. Okay, most of the coast region Huang diffusion like 10 to -2 meters square per second. You know how much they use? They use 10 power 7 meter per second. So that means they can diffuse water very quickly for every place they want. Right? So that's why a lot of model, if you don't know much physics, you can really misleading. Okay, that's why the criteria you said how to, you also ask what is optimal size, right? Your size depends on what question you are. You don't have an optimal size depend on the question you address. Okay, so like we did one, for example, we do the one with a coarse resolution model. We know the geotraffic circulation. 10 kilometer resolution is sufficiently in the open ocean. Right? So if you have a nesting boundary open ocean, 10 kilometers probably is good enough. You see, depending on the circulation for larger domain model you resolve. So you don't want to set your boundary was reaching the larger domain, the boundary over there. It's not truly resolve your physics. Right? For example, you have a Gulf Stream, you have a western boundary crucial there. The crucial's wave length is about 100 kilometers. Wave length. Right? So your open boundary should at least 10 kilometers. Right? So if you 30 kilometers, you get a crucial, but not very, not get a grading correctly. Sea level grading. That's a use 10 kilometer solution. Then you nesting on a crucial in the boundary there. That should be 10 kilometers, should be fine. But you get a high resolution is better, but you don't want it too high.
Okay.
Okay?
I think every students have a question, so
Yeah.
I will not interrupt. Okay.
Okay.
So
Yeah.
do you have another?
I try to
Yeah.
answer King's question. Right?
Yeah. So yeah, go on, Junyoung. Do you have another question?
No, that's it.
Okay.
Thank you for your detailed explanation. Thank you.
Yes, thank you, Dr. Chen. Any other questions?
빨리 하지, 윤지가.
Yeah, I have one question about the groundwater module.
Mhm.
I think I show my research to the Professor Chen maybe 1 year ago. I study about the meltwater effect in Arctic field ocean, and the meltwater are are discharged at
Yeah.
the bottom layer
Yeah.
like this.
Yeah.
And I want to know what is different between TC method
Yeah.
river input at the bottom layer by using TC method and method 1 groundwater discharge. Yeah.
Now groundwater, you put a transport at the bottom, right? So that's
Yeah.
why it was a common thought. Also, you got a two groundwater module. One groundwater module, you assume you had a directed groundwater come in from the bottom, had a water get into the region water. The second method, so we said no, because groundwater amounts very small. Groundwater amounts too small based on the freshwater amount. So we only consider, we ignore the volume, okay, ignore the volume. But we know when the groundwater here, they change the, they will become fresher, they change the density. That's why we just want to make sure the density was grading, density was conservative. We consider mass changes, but don't consider volume changes. That's what a method 2 was doing. Okay, method 1 is direct put transport into bottom. That was a very straightforward method, right? So we also put the groundwater in the node point. The reason because it's come from W. Because we calculating the vertical velocity W was 8 bottom, and now we at a node point. Because it's water conservation node point, put a W there. That's why you get groundwater, you also put it in the node point. You cannot put it in the cell. Because the W was the W velocity was in the node, right? So you need to consider control volume, groundwater there to put a point. That's consider the whole, because when you put it in, they times the area, control volume. That's what the groundwater is. So then you compare with a river discharge method, it's different. River discharge method, the water come from lateral boundary, come from coast, right? They was go to the whole water column. You can get a partition of the water, the surface of the bottom, but all come from lateral boundary, not come from W.
Oh, okay.
That's a different. That's why, also, freshwater input, output there. So they use like a two method. One is called node point method, just like a picture show here, node point. That's entry the one, you mentioned the one here. So that's what happened. They just dump the water into the node, into the water there. So then they had a continual equation calculated, right? They calculate what the sea level change. The sea level build a grading. The grading push fresh water go into the domain. But they just dump the water. They see if I put a volume, call it volume flux there, because you sea level based on the net volume flux, right? Net volume flux determine the sea level changes. That's why you was dump the water in, your flux changes, the sea level can go up. Then they build the water in. So the second method there, so they said, no, I don't want it this way, because this way, sometimes not coming good, because, you can sea level build up, but then if you put a very upstream the river, you have to build a very strong sea level that can push water down. Sometimes sea level can be high, not, higher than you observe, because you need to put the water in. So another way they use the called momentum flux. That's why they don't put the sea level node point, they put the edge. Because each node has two edges, right, connected. In the edge, they put the velocity transport direct into the region, change the velocity momentum. Then momentum changes, then velocity changes, then change the sea level. But then, which method is good? When the resolution becomes high, two methods converging. When the resolution becomes high, the high two methods converging same. Okay. However, if the river flux is very small, you better use momentum flux method. Don't use the sea level method, because sea level method they can put the water in one point. It can be very low salinity come out one point. They can build a pressure grading. The pressure grading can be unusually high. They can cause the buoyancy circulation locally. Particularly it happen for resolution low, right? But the momentum method, because they push the water, dump the water in there quickly, they don't build the pressure grading there. So when the fresh water is smaller, right? So you better use the momentum method. Okay. So we was recommend, but no, the point is easy. Because the momentum method, you have to divide the two. You want to make sure each side how much you transfer they are, right? But you specify the motivate automatic calculation for you. But node point here, you can directly just put a node. That's very easy. So that's why some model we do when we do the calculation. So between resolution, we put the fresh water in. We want to see does the real pressure cause the local pressure gradient larger. If not because when the fresh water very larger, you don't have a problem, right? Because they can quickly distribute the water. That's why you don't build this. Very big show is when the fresh water charge very small. That can cause a problem. Okay.
Okay, thank
Answer your
you.
question?
It was very helpful
So that's why
for
for the
me. Yeah.
water, for your Arctic Ocean region, so I talk like a like a Q1. So now we do the 3D wash method. When we do the 3D wash method, we think we should include the Arctic Ocean model. That's my proposal. We have already had a ice sheet model.
Yeah.
But now you do the Arctic Ocean model, you have a lot of ice come from land, right, in your region. But then you put like a non-polar source around the region there. If you have an ice sheet model, so you can see how much time they can melt in the ice, the water can continue the time dependent water coming in the region. So that's probably make more sense.
Or you mean that if I coupled
Yeah,
FVCOM and
FVCOM.
iSheet?
Yeah, ice sheet model because some people Norway group already did that.
Oh,
But
I read that paper.
they already done
and
that, but they use a different coupler, okay?
yeah.
So then what Q1, now he working on the 3D was, after 3D was finished, so he will apply the article ocean model for data simulation. Then meantime, he can include, I think it's iSheet model, so make the article ocean model more relaxed. This can use your case, right?
Yeah.
I think your work's nice. You get a lot of data. You should publish the paper, good paper. Okay.
Actually, Yunji is kind of finalizing the papers, and
Oh,
we're
good,
going to I'm going to include you as an author.
good.
So I will send you a draft.
But I can help you to editing the paper.
Yeah, yeah. So I will talk to Yunji
Okay.
after. Yeah.
Yeah. Well, you
Okay.
got a lot of data, excellent data. Okay.
Thank you.
No.
Okay. My question is finished. So
Yeah. Okay. Good.
Oh, any other question?
뜸들이지 말고 빨리빨리 김영희가
Yes,
하지
right.
그럼.
I have a question about ESMF and 1A nesting.
Yes, please.
Uh, in the lecture, it was mentioned that 1A nesting can be implemented by adjusting in feedback domain during ESMF nesting. However, I understand that FVCOM has its own 1A nesting function in an option in name list. I think the difference between these two approaches is that with the name list simulation needs to be run twice, whereas using ESMF allows the simulation to be conducted a single run. Is this correct? If not, I would like to understand how the simulation is performed in each case.
Okay. I probably can address the question we test about. Okay, that is another nesting way. That's called that's the coding we develop ESF for two-way coupling. You had a two-way model, you had a run a larger domain, a small domain model. So you want to exchange data and the two model, okay, two-way nesting. We had a paper published in 2018. Dr. Here's the publication, the paper there. Okay, so then what happened? So you had to be, you had to be in the coding you set up a nesting, but two-way. before we talk about the nesting, before the first one, the king's question, his word is come from one direction, larger domain to small domain. Don't consider feedback for small domain to larger domain. But this one, ESF to the two-way coupling, but meantime, they also can use the one-way, right? Can use the one-way nesting. You see what the difference with the one-way nesting, use the nest, and one-way nesting at FVCOM? Yeah. One-way nesting in the ENSF, two models run at the same time. So for ENSF one-way coupling, right? So your
Yeah.
big domain model, small model ran at the same time, but only had a big model give the small model, okay? The data, but there's a two model run at the same time. But then one-way nesting for use only for FVCOM. So boundary condition is giving one way. So they don't run the parallel. Okay, your big model run first. You output the boundary condition put in the, add is a boundary condition for small model domain, run again. That's different. You understand what I said? But for the ESF, because ESF is developed for two-way nesting. You have two model, large domain model, small model, same runtime. So then the small model data give it to big domain gives small domain. Meanwhile, they also can run for one-way nesting, but still run the two model, right? But only get a big one to a small one, but both model at the same time, they don't save the data. Like a one-way nesting for FVCOM, you run a big model domain, you FVCOM had a function like the output the nesting boundary, right? So you had a nesting boundary for output for big domain. So then when you run a small domain, restart a small domain again, small domain after the big domain finish, then use the output boundary drive your model. So then you can a boundary condition sieve into the file. But when you do the ESF nesting, even do the one-way, they don't save the data. Okay, because two models run at the same time. So then the big model give the small model data. After they continue run. They don't save the data. Okay, the two model is parallel running.
So in terms of
Yeah.
computational efficiency, the ESMF way is better.
No, it's dependent. The first thing, if you use the ES way method, so you had to consider more node because you need a two model, small model at the same time, right? For example, you had a 20 node, so you probably need to spend a 5 node for big model domain, and those 15 node for small domain, right? So for forecast system, it's really take a risk. The reason because they don't save the data. If you run in the model at the same time, and they download the data something, breaking, your model stop.
Yes.
You have to rerun the model everything again.
Right. I see.
But then one-way nesting only for FVCOM because you run the big domain model first. You have a nesting boundary, right? So if something happens, you just rerun a small model. You don't need to run a big domain model. Also, you can easily look at the open boundary condition, what really happened. So see on the boundary condition is compare with data, how good they are. You all compare. But two-way nesting method, yes, you couldn't do that. Because they automatically exchange data between the node, okay?
So
That's why for forecast system, I don't recommend that method unless you are really rich. Right? Unless you get a supercomputer all by run your lab, that's why you don't really care. Right? You should run this way because you don't see what data can rerun again.
yeah.
But
Nice.
we has been put our model in the forecast since 2007. So we found frequency shut down. because sometimes you download the data, may not data had a problem. Sometimes our computer node had unstable, right? So then sometimes some internet issue, you frequently shut down. So you have to manually restart again. So if you use ESF method, you have to restart everything again.
I see.
Mm.
I see.
Also, we found, like we do the forecast system, where co-simulation model take about a couple hours to run it for 3-day forecast. However, with regional model only take a 2 hour, 1 hour can be finished, right? That's why we want to run it separately, use the nesting boundary, run a second model. This way, because the big domain model don't take a lot of time, right? So then we also can put more node for small model domain.
I see.
Okay?
But for the two-way coupling, we cannot avoid using ESMF.
You had to use that.
Have to.
You had to use the ESF. The ESF, the big reason because you had to exchange data of kind of force back.
Right. I
Okay.
see. I see. Thank you.
Yeah.
다음
Okay.
질문.
Thank you.
So
I understand about it.
So some people think about a coupling with Julia. Today at the MIT professor to give a talk, I missed the talk. He was to talk about he developed a non-congested model for the Julia program. Because a lot of young people know the Julia Python.
Yes.
The Python cannot parallel whatever Julia can do. So but we don't have. I really want to have some Korean student computer science. You can find so we can cover FVCOM to Julia. All right, that should be exciting. If you had some student like to do that, that's wonderful. So then you can have a South Korea FVCOM version.
Okay.
I think the Julia version is better because a lot of young people, young generation, not learning for the fortune anymore. But they Python, but Julia get a parallel, right? I think that's very good, help people because they already had a model developed by Julia. The program we can take their, the way they do. We can follow the framework they do. Can do it quickly.
Does that Julia also have a nice numerical library or something?
Oh yeah, a whole lot of library.
Oh.
They get all the MPI, all the library. The Julia can be integration library. Also, they have their own library. That's why
So,
when you do the Julia, you don't need to install this library again. They already include.
so in terms of floating point calculation, the Julia is kind of better than Fortran?
Li Siqi can answer this question for you.
Professor Wu, so actually it is not as good as Fortran, but it has Julia has a similar performance on simulation as Fortran. So which means that if we do a ranking between different language, so Fortran should be the first top one, and then is Julia. So after that, maybe MATLAB, and the last one is Python. So roughly this one. So yeah.
The advantage of using Julia over Fortran is because of parallelization.
No,
So
I know parallelization is similar, but only they can use the GPU.
yeah.
Oh, I see.
Yes. So because
GPU, I see.
Because
Okay.
Julia can already turn on the GPU.
Oh, yeah. Then definitely is advantage. Definitely. I see.
That's the most advantage because they get GPU already pre-installed Julia. Okay.
I might suggest.
But you also can use GPU as a Fortran, right? Doing some coding like GPU, but the problem is still a lot of data storage exchanges, a lot of problem. But Julia, this one they had developed. I don't know much about it, but I just say it's probably better.
I see. I might talk to the professor in the AI department because I'm one of their faculty member.
Yeah.
So it might be a really interesting suggestion or proposal.
So if we have some student, graduate still like to do, so we can have, we can explain the coding to you. Then you can MIT version copy, so we can convert FVCOM as a Julia.
Yeah, there'll be another way of wonderful. Yeah. Great. Okay.
So, yeah, we want to do, but we don't have a lot of we don't have the time. But now the U.S. situation right now, whole university probably all shut down very quickly. So so they get a lot of change. Later I talk to you about this. I don't want to take the class time to talk about that.
예.
Okay.
예. 다음 민우 아니면 지명이 빨리빨리 질문.
제가 먼저 하겠습니다. 잠깐만.
I try to pronounce it called Jingyong, right?
My name is 지명.
What's name called Jingyong?
email.
Jingyang, okay.
It is difficult to pronounce.
No, we
Uh,
learn, okay.
So can you see my slide?
Yeah.
So my main question is about the core. So you show the slide 7. The core used the modeling of curve similarity theory,
Mm-hmm.
and you showed the slide 8.
Mm-hmm.
You showed 5 cases of the data with no
Yeah.
correction, and you show one case of using core. So I wonder is how much did the modeling of curve similarity theory improve the heat flux is.
No, I probably can address the question. So, the issue, for why we use the core program, because we want to improve the heat, flux calculation, most lantern and central heat flux, not short wave. Short wave is not hard to, flux calculation, because that's related to the skin temperature in the sea surface. The skin temperature, just like, because most calculation heat budget before, they use 10-meter high wind, 10 meter, you got a weather model, they was convert everything to 10-meter high. Right? You look about the wind equation, like 10-meter, wind speed times like a CD, right? But then what happened now? So in the between the 10-meter to the sea surface region, so they get a called a thermal boundary layer, the very thin boundary layer there. This boundary layer can be for unstable weather. For stable weather, doesn't matter. But when the weather is unstable, like storm come here, a storm, this is going to change of between the sea surface about 10 meters can be significantly. So then you look at the heat budget, right? Look at the heat budget. The heat budget should be really calculated was between the sea surface and the water, air and sea phase, right? So boundary, interface. But then the temperature difference should be equal at the boundary as air at the boundary was interface, also water was on the same phase. Because this temperature is not a continuous. Right? In the temperature, in the sea surface, air temperature, water temperature is a big gradient. But you look about the central flux. Central flux really depends on the air sea temperature different. So if you use the wind, heat temperature and 10-meter or some other depths there, height there, so your air sea water temperature difference probably not accurately represented that. That's the reason you can overestimate your flux. Right? So that's the reason we find a model for instance, if you use the Wolf model output directly, right? So that's why they don't consider skin temperature. That's why you see the overestimate, particularly for unstable weather condition like storm. Right? So you look at when the weather is good, you see the very similar. Right? So that's the reason. So key issue, that's a similarity theory, is trying to, do the iteration, the method, to try to let you resolve the skin temperature at the sea surface. So in this way, you can get a better representation of the air sea temperature difference. You can better representation on the bottom of the sea surface roughness. Right? Also the heat flux, and the wind, because evaporation proportion to your wind speed, right? but they can resolve the sea surface wind speed for you instead of 10 meters. Okay, this whole theory calculation is just everything that you go get improve your representation of the sea surface weather condition. You know, that's called skin temperature. Right? So we talk about air temperature, but they call it skin temperature, just between the interface temperature in the resolved. So this way, that's why they have some kind of imperial equation. No, you have to, iteration, the program running to get a skin temperature. When you get a skin temperature, you can see the, wind stress. That's instead use, 10-meter wind. They use the wind start, right? In the wind start, fraction velocity in the surface. Then instead of like central heat, you see the temperature. They don't use the 2-meter or 10-meter with the heat flux, the temperature. They use the temperature difference, just what in the sea surface start. Now all these things here, the calculation method still same. Like if you don't use the boundary, you can use 10-meter, right? 10-meter wind, you calculate wind stress. That's what people use, right? You look at when every border condition, you use 10-meter wind, right? Times the law, you can get a wind stress, right? But now we use not a 10-meter wind, we use a wind, fraction velocity, bottom of the boundary layer, the wind. The whole series is very complicated. Let's tell you how to do that. In this way, you can more accurately resolve. Okay, wind speed. After result of wind speed, you can resolve the temperature, air temperature, skin temperature. So then you also can get the skin of those kind of because of the water vapor, the pressure, right? As a humidity, relative humidity. You get humidity related to the it's kind of evaporation. So then you include this one, you can get a better result. So that's the reason it's a core method doing. Okay. Before, everybody know, okay, the model, minority model, not able to resolve the bad heat flux. They know sometimes overestimate 200%, but no one will do any work there. So I told I'm the person introduced the method into the ocean to apply the recurrent heat budget. After this one, I talked to the NCAR people, asking they change the WRF code. They don't want to change it.
Okay.
Okay. Yeah.
Actually,
So
actually,
interesting. When I had one mineralogy professor was in the Stony Brook. He was responsible doing the those kind of climate change, the warming condition for air in the New York City. First WRF, every time he was easily overestimate, easily underestimate. Now after he put my subroutine into his coding, he said the compare data really good. So then he write a letter to NCAR. He said the letter changes this way, but NCAR people said no. Because this core program is come from, you don't know the core program, the full name? It's called this is called air-sea interaction experiments in the equator, was in the equator region.
oh, I see.
So we had they make a 10-year measurement nearby nearby equator. So then they measure the air, measure the water. So then they use is similarity theory, most of those polarization. So then they come out a very good heat budget calculation method. Okay, so ocean people really like it because it's based on observation. Right? Basically, they come out of 10 years data measurement. Now it's more. I think this program probably will stop. Okay, right? That's come from a lot of buoy data. Come from this method really accurate.
Yes.
Because the equator region is good to testing because this region, the wind like the force back like a northeast wind, like a southeast wind coming there, they're also reaching a lot of converging, right? That's why a lot of unstable weather, that's a good thing to test that, okay? So
Another interesting topic that we would like to study is the LC interaction near the tidal flat.
yeah.
So do you think that this core algorithm is also better near the very shallow region like tidal flat?
I think this method should be better because at least they consider skin temperature. They not consider 10-meter temperature, 2-meter temperature.
Yeah.
You know, most the temperature sensor measured in the ocean is about 2 meter. No, they put like a sensor of the 2 meter, right? They calculate, but the wind sometimes can different depths, different height, can 2 meter or something because the buoy, right? You put a buoy there, they measure 2 meter. But most of people use the wind driving model for wind stress calculation. They use a 10-meter wind. They use a 2 meter, then they convert to a 10 meter. So in FVCOM, we use a larger than pound method. We use Smith method. Larger pound method is barometric method. Don't consider unstable weather condition. The Smith method consider certain unstable condition. But I do feel like this method is better. Okay. That's why, this method, that's why FVCOM have the 2 way to put the wind stress into the model. One is called wind stress, use this method because you do recalculation. Another was wind. But if you look at the wind, it still use 10-meter wind. Only do the heat budget, you do this method, but put the FVCOM wind forcing still use 10-meter wind. Right?
Okay, I understand that. Thank you.
Only have 8 minutes left, okay?
Yeah, I think we still have time for one last question.
One question.
I have a question. Can I share my screen?
Yes, please.
Okay. My question is similar to Jim Young's question, but I will ask my question. I want how surface lowness created by wave affect wind stress and drag coefficient. I think that surface lowness likely influence not only wind stress but also heat flux exchange between air and sea.
Yeah.
I wonder how surface lowness affect heat flux calculation, either through equation or parameters.
This is done by Dr. Li by this method, okay? You see that the problem we have right now, our wind stress calculation and the model is different from heat budget. Okay, heat budget, we use the skin temperature, doing the calculation, do the heat budget, the core, right? So then when we do the really ocean case, like with driving forcing, like me not driving, we still use a 10-meter wind, right? So that's the problem. So the most, we consider here is the bottom, surface roughness, right? That's different from the heat budget calculation. This one really calculates skin temperature, the skin roughness, right? So this method for heat budget calculation, we should be consistent to put together, right? But a lot of people don't, because if we really want to use this kind of method for the course, right? We should be replaced all the method of wind, but now we separated it. Okay, so then that's the bottom roughness, surface roughness there. So it's really critical. They consider about certainly a similarity theory, consider like a cause. The cause one, I don't think we include a wave, right? I don't think we include a wave, cause one. The cause program don't consider wave because of heat budget, right? But really case of wind stress here, so for the surface roughness, they have a wave can change significantly surface roughness, right? Depending on the wavelength, right, and the frequency. So that's why, but roughness changing the wind stress, it can be changes. Okay, so this all come from empirical equation, right? So they just do the laboratory experiments, but not laboratory, just like a ocean LC attack, measure the winds, how they affect it, a lot of permutation, things there. So which one is correctly? That's Dr. Lee was summary here. You get a wind only like a larger pond, 1981, right? This is just based on the parameterization to not consider unstable condition, right? The core program, you see the core program, the bottom roughness over here. You see the core program we include here, this way. But we use the program. This all come from the fraction with velocity, right? So they also consider about the bottom boundary, but don't consider wave. Right? Don't consider wave, okay? So then we have a one way, consider how the wave affected. But so this way, this method called core program, really core program, but the roughly is iteration. You run iteration many times, right? So then the update, but the formula like this way show here on the left side. But however, inside how to calculate it, because it's fraction velocity change with time. Iteration, they keep changing, get it back to one. But here you just get directly get this formula is here. Okay. That's different. You can combine together. We're not doing it right now. We just use a different formula. That's why I was mentioned before. I said, for the heat budget calculation, we really use the skin temperature, skin relative humidity. Then we use the fraction velocity A the sea surface. Then we use the wind stress A the sea surface. But when we drive the model for the outside boundary forcing, right? It's not like a like a heat budget anymore. So then we still use a 10-meter wind. You see here 10-meter wind, right? That's two different, separately different. One is actually forcing, right? So then we base where all the change over here, the different is the surface roughness. But then we consider about the heat budget, that's different. Okay?
Okay, I understand.
Here I want to add something more. So these three parameterizations were first discussed in one paper from John Warner's laboratory. So I included this reference in the chat. If you're interested, you may check it. So when we after we read this paper, we also include all the three parameterizations with wave roughness and the wind into FVCOM. But however, the problem is that there are two methods that include the U star, which is velocity at exactly the air-sea interface. So in FVCOM, because we do not know this variable, and also usually when people run FVCOM, we do not prepare this variable. So we have to include the call program so that we can let the call program to calculate the U star. It's not because that these methods need the heat calculation. It's just because we need the U star.
Yeah. Yeah, just get a U star. Yeah, that's your point. Get a core port, 2.6 port. Yeah, it's come from a core program. Yeah.
So in other words, like Professor Chance point out, to update this core program for including the wave effect, that means the U star need to be changed, including that wave effect. Is that right?
That's something we should consider because for heat budget calculation, roughness also can be changes significantly, like a skin temperature, or exchange heat budget changes. But then the problem though, that's you start, you start put here, it just depend on the fraction velocity, but how you include the wave into the similarity theory, that's a challenge. Because this is all based on the similarity boundary condition, there, but you need to put a wave. That's why surface boundary condition changes. So how you can update the weight, that's really challenging,
Mm.
right?
Mm.
And that this can really improve a solution we don't know. It's a solution we don't know. Because there's kind of two different approach. One is called fraction velocity, like a similarity boundary layer theory, right? Boundary theory, like flexion, like a log layer, something like this. But this one is a way with called S interaction. Right? It's a little bit different. That's how you do that. It should be do some physics first, okay? Right? How you can get the surface boundary thermal boundary include the wave, right? I think you definitely doable, but just but sometimes you develop some theory, you have to have the data approved. That's the problem. Measurement data really approved. Massive scale data, you have to pay the high frequency tau there to get the data measurement. Okay. Yeah. Good. Okay. Time is
Okay,
up.
Yes, thank you. Is there any other question?
Yeah, you can please upload your question on our class discussion board. Right? This way, student ask a question, for future people can reference question.
Right.
I think your people doing a very good job, and the students do a very good job, very organized. Okay.
Yeah.
Excellent.
Okay.
Yes, so currently all the questions have been uploaded on the discussion board. So if you want to review them, please feel free to come here. And if you have more questions, please read them up here, and Dr. Chen and I will answer them as soon as possible. And so thank you so much for joining the discussion today, and see you next week.
Yeah.
Yeah.